Okay, so let us now start by discussing what is probability. Okay, how do we define probability? So, if you go to classical textbooks of probability, you will find definitions of probability as the science that studies chance phenomena. Okay, so essentially we have to understand what is chance phenomena, what is chance, okay, and then you can ask yourself, well, is a financial crisis a chance phenomenon? Is an earthquake a chance phenomenon? And or even is the toss of a coin a chance phenomenon? So if you take a coin and you toss it, well, is this really a random phenomenon or not? Well, actually, if you are able to get full information about the position of the coin, the force that is impressed on it, and you can integrate the laws of motion, Newton's equations, then well, you can find out whether a coin that is tossed will turn out to be head or tail. Okay, so where is the chance? Okay, there is no chance. So there is chance only because there is lack of information, because we don't know this information. Okay, so indeed this classical definition of probability has been replaced by a more modern view of probability, which is much closer to information theory, and to really reflect this aspect that probability is really about lack of knowledge. But so indeed, say for any possible event that we may be interested in, let's call it A. So all we can, because of this lack of information, all that we can say is, in many cases, is what is the probability that a particular event A will occur under certain conditions omega. Okay, so this is the only thing the only statement that we can make in many situations. Okay, and it is important to recognize that the probability does not only depend on what we are interested in, on the event that we are interested in, but also on the conditions under which, or what we know about the condition under which this event is supposed to happen or not. Okay, so this is what is going to be called our state of knowledge. And so generally the probability is a function of both these two things. So in most of what we will do in this class, we will just write this as the probability of A, because we will assume that our state of knowledge is fixed and does not change. But of course, you can see that if you are interested in understanding whether tomorrow it will rain or not, then knowing a lot about meteorology will of course change a lot your estimate of the probability that this may happen. Okay? Okay, so how do we define probability then? Okay, so one classical way of thinking about probability is as the limit of the frequency. So in this case, what you think about is that under the same condition, you repeat an experiment many times, n times, and you count the fraction of times that the event A occurs in all these repetitions, in all these trials. And then you define the probability as the limit of this frequency, but in the ideal limit where you can repeat this experiment an infinite number of times. Okay? Okay, so this is not a reasonable definition of probability because of the following fact, that if you really look at what mathematically this statement means, it means that for any however small number epsilon, so there must be an n bar such that for any n larger than n bar, the deviation of the frequency from its limit, which should be p, should be less than epsilon. Okay, but this, if we are really talking about the frequency of a repetition of experiments, this cannot be true. I mean, there can be very special sequences of experiments where essentially this inequality is violated. Okay, so at most what we can say is that the probability of these violations is going to zero as n goes to infinity. Okay, that these violations will be more and more rare, okay, for any epsilon positive. Okay, but then you see that you are defining probability in terms of probability. So this is a circular notion, and of course this cannot be a good definition of probability. Okay, so this also shows that to some extent probability is a primitive concept. And this is also clear because we have, from the point of view of neuroscience, because we have areas in the brain that are dedicated to computing probability and other probabilistic concepts like risk, etc., etc. And so, this means that probability is not something that can be defined in terms of other mathematical concepts, but it's a primitive concept. And so what we need, if it is a primitive concept, is we need axioms. And essentially what we will describe are Kolmogorov axioms. So this is not the only way in which one can give an axiomatic definition of probability. There are different ways. But in the first part of the course, we will mostly be concerned in doing calculation. And so Kolmogorov axioms give us a framework which is very clear and precise, and allows us to deal with problems in probability in an unambiguous way. So this is what we will follow in the first part of the course. In the second part, we will see another possible definition of probability. Okay, so common general axioms are based on three objects. That I'm going to describe for you. So the first one is what is called a sample space. So this is the space, this is a set whose elements are all possible outcomes or all possible things that may happen. Okay, all possible outcomes of an experiment, all possible states of the world if we are interested in a prediction, etc., etc. And a subset of this sample space is an event. So we will say that when we in a probabilistic setting, so one of these outcome will realize, and if this outcome belongs to event E, to the set E, then the event E will occur, otherwise it will not occur. Okay? So then the second thing that we need is this object here, which is just a family of subsets of omega. And this family is should be such that omega itself should belong to this family, and that the complement, if A belongs to this family, then also its complement belongs to A. So usually you have this Venn diagram type of graphical notation. So if this is the set of all possible outcomes, then this is an event A, and all the rest is the complement of A. Okay. And the third thing is that if so, this family should be closed under set operation. So if A1 and A2 belong to A, then their union also belongs to A, and their intersection also belongs to A. So, so what is the union? Well, if these are two events, then this event here is the event that either A1 occurs or A2 occurs. And the intersection is the event that both A1 and A2 occur. Okay? So the idea of this definition here is that A should contain all the events that you may want to talk about. So if you, and it says that if you want to, if you are interested in event A1 and A2, then you should also be able to talk about the event that either A1 or A2 happens, or that both A1 and A2 happen. Okay, and if you are talking about an event, and then you want also to be able to talk about the complementary of this event, so the event that this event does not happen. Okay. So this is a little bit like the dictionary, that this A is like the dictionary of the things that we are going to discuss in probability. Okay, the last element is P, and this is a measure. It's a measure which is defined on A to the real numbers, and it associates to every set that belongs to A real number which is P of A, and this satisfies three properties. So the first one is that P of A must be non-negative. Second is that P of omega must be equal to 1. This is called normalization. And the third thing is that what is called additivity. So that if you have a sequence of events which can be countably finite, then the probability of the union of these events is equal, and you have that A1, and these events are all disjoint. Okay, so their intersection is the empty set. So if these are all disjoint, then their probability is the sum of the probabilities. Okay? So this structure allows you to discuss probability, and the reason why I'm discussing this is not for mathematical rigor, but because it is, as we will see, it is useful to go back to this structure when we want to be sure about what we are doing in our calculation probability. Okay. So many of you will have already seen these things. For example, from these properties, you can derive many other properties. So, for example, it is easy to see that the probability of the complementary of an event is equal to 1 minus the probability of the event. And why is this so? Because the complementary of the event, the union between the complementary of the event and event A is equal to omega. These two events are disjoint event, like this one. So the sum of this and this should give you the probability of this, which is 1 by normalization. Okay. Also, another property that you can derive easily from this is that the probability of the union of two events is the probability of one event plus the probability of the other event minus the probability of the intersection. Okay, and how do you do this? Well, if you have these two events, A and B, so essentially you can write that the probability of A union B is the probability of A union with B but not A. Okay, so with this part of B which does not belong to A. Okay, and this is clearly the probability of A plus the probability of B and not A, because these two events are disjoint. And the probability of B can be written as the probability of B but not A plus the probability of the intersection. Okay, so the probability of B is the probability of B but not A plus the probability of the intersection, which is this one. Okay, if you combine these two, you get this result. And so on. You can derive a lot of relations from, I mean, you can derive all of probability, you can do calculations with this using this setting. So why is this important? Okay, so it is important because we have an intuition about probability, and this intuition sometimes is right, but sometimes is wrong. And so there is a whole field which is called behavioral economics, which studies how people behave in a way which is not rational, or people, how people miscalculate probabilities or estimates risks. And so it is important not to rely on our own intuition. So let me give you an example. So a simple example is, imagine the following problem. I give you a circle, and let's pick 2 points, say A and B on the circle, okay? And let's ask the question, what is the probability that let's call AB the arc that does not contain the origin, so this one, so this is AB, and let's call BA the other one, okay, the one that contains the origin. So what is the probability that AB is larger than BA? Well, you will say, well, I've chosen these 2 points at random, so there is no reason why this arc should be larger than that other arc, so this should be 1/2, okay? Okay, but so what now what you can do is use Kolmogorov axiom and ask yourself how do I check this result here? Okay, so the first thing that we have to do is to define omega. So and one way to define it is to say, okay, so let's define the angle alpha for A and the angle beta for B. Okay, and then this tells us that the sample space is actually the square 0 to pi in each of these. It's the square from 0 to 2 pi. Both alpha and beta, okay? Because this allows you to specify any possible outcome of this in this problem, okay? Now, essentially, you have to compute. You have to ask yourself, what is the probability P? Okay, how do I define the probability P? And okay, so imagining that I take for A the set of all possible subset of this set, but just for simplicity, it's intuitive that we are going to take a probability for which any any point is equally likely in this square, okay? Or if you want any set, so the probability that alpha and beta fall in a particular set A is equal to the area of this set A, okay? So then now we have to compute what is the what event does this condition corresponds to, okay? And you have to work a little bit with these angles, but in the end what you find out is that if these two angles are between these two lines, are in this region here, then this event does not occur, okay? So this event E is the union of this part and this part. And so now what is the area of these two things? Well, you can compute it very easily, because this is essentially 1/4 of the whole area of the square. So the right answer is not this one, but rather it is 1/4. So our intuition in this example is wrong. Okay, at least my intuition. Okay, so why it is wrong? Well, the reason why it is wrong is that essentially in this problem there are not 2 points, but there are 3 points. Okay, and because there is also the origin, because I'm computing all these angles from this origin. Okay, so and when I ask this question here, I'm asking whether this arc, what is the probability that this arc is greater than the sum of these two arcs. And by symmetry, all these 3 points are distributed at random on the circle. So it is natural that typically, generally, this arc will be smaller than the sum of these two arcs. Okay. Okay. So the other thing I want to recall is that also these Kolmogorov axioms are important to understand what it means to draw at random. Okay. And this is explained by this Russell's paradox, okay, which is not a paradox, of course, but so the statement is the following. So take a chord at random in the unit circle, and then we compute the probability that let's say that this chord is larger than the side of the inscribed equilateral triangle. Okay. So it looks like a very easy question. So there is a chord. Let's call it AB, and then there is the equilateral triangle, inscribed in this circle. So this is a circle of radius 1. So we know that this chord, let's call it CD, this side of the triangle, the length is square root 3. So we want to understand what is the probability that this chord is larger than square root 3. Okay? But the real issue is really what it means to take something at random. Okay? Because there are three ways in which you could do this. Okay? So the first one is, say, so if you take this chord to be, so by symmetry you can always rotate this thing and take this chord to be horizontal. Then if you draw the vertical diameter here, so you can figure, you can find that if these points fall in the middle part of the diameter, then the chord will be larger than the inscribed, the size of the inscribed triangle. Otherwise, it will not. Okay, because because I didn't plot this properly, but if you plot this properly, so you have this lower side of the triangle cuts this thing exactly in the midpoint between the origin and this point. Okay, so it is clear that if you do this calculation, then the probability that these points fall in the middle side of the diameter must be equal to 1/2. Okay, but there is also another way to answer this question. That is, so let's take this chord now to be such that A also coincides with the vertex. Okay, so this is A and this is B. Then you can argue that, well, if this angle here, if alpha is between pi over 3 and 2 pi over 3, then this chord will be larger than the side of the inscribed triangle. Otherwise, it will not. Okay. So what is the probability that this happens? Well, this probability is equal to 1/3. Okay. So, and there is even a third answer to this question, which is if you just do a different argument that gives you 1/4. This is in the lecture notes. Okay. So the reason why you get a different answer here is because essentially you are choosing a different sample space in each of these three cases. Okay, so in the first case you take this line from -1 to 1 and you look where this chord crosses this line. In the second case, so in this case you take omega to be -1, 1. In the other case you take omega to be just 0 pi, so the angle alpha that this chord makes with the tangent. And in this other case you take omega to be just the area, the interior of the circle. Okay, so it is clear that if you take a different definition of the sample space, and then you are going to get different answers. So it is very important when you look at a problem that you ask yourself, what is omega? And what is and how is the probability defined on this omega? Okay.